start. All right. Welcome to this ICC seminar. We have here with us David, who's going to talk about the rise and fall of black hole chemistry. Please go ahead.
Yeah, thank you so much. Hello, everybody, and greetings from Prague, although it was supposed to be greetings from Canada, but in the end, it's from Europe. And then I'm going to tell you about the rise and fall of the black hole chemistry, and not really, but I will try to explain what I mean by this. But of course, the analogy I'm drawing here is with the rise and fall of the Roman Empire. And we shall see that black hole chemistry reached its peak at some point, and then since then it's sort of declining, and we shall see what happens in the future. All right, so here is the plan of the talk. So first, I will tell you about the rise and what was great about black hole chemistry as a new subject. And then I will tell you about its problems, and namely that was to basically interpret what's happening in ADS bulk with variable cosmological constant on the CFT side. On what is the corresponding behavior of the CFT on the boundary. And then I will basically formulate like a new dictionary, the extended holographic dictionary for what's happening if you have variable cosmological constant. That will give me an opportunity to study the CFT phase transitions, and then I will return back to the black hole chemistry, now upgraded one, but we shall see that as formulated before, it is not so nice anymore. All right. So now this talk is based on 3 papers. One is very old one here, 10 years old, and then these 2 are quite new, past year. But the truth is that I still don't know really what to think about all this, and so I will ask for your opinion, and I will ask if you have any comments, or you just tell me that this is all nonsense or whatever. All right. So the rise of the black hole chemistry. So the black hole chemistry is based on a very simple idea, and that is consider an asymptotically ADS black hole space-time, and we identify the cosmological constant with the thermodynamic pressure, as you would in for the normal perfect fluid. And so we will have D, capital D will be number of space-time dimensions, and this is the formula for the corresponding pressure. And then what is unusual in the black hole chemistry is that now you allow this pressure, this cosmological constant, lambda, to be a dynamical quantity. So here I am still fixing the gravitational constant G, so the only thing which is dynamical is lambda, and that gives me the dynamical pressure. Of course, because I am in ADS space, lambda is negative, and so that's why the minus here, so that gives me the positive pressure. So now this idea that you can have dynamical cosmological constant, it goes, quite back, and so it was first proposed by Teitelbaum and Brown in the 80s, and then many people formulated various mechanisms how you can make effective cosmological constant to be a dynamical quantity. All right, so that's the simple idea. So now if you allow this, then there's several immediate consequences which immediately follow from here. So first of all, you may look at the first law of black hole thermodynamics, and as shown by these people over here, you pick up the term. You have the standard terms in the first law, plus you have some term where you have some quantity times this delta of pressure. Of course, by dimensional analysis, you can immediately realize that that quantity has to be the volume. So suddenly you have a VDP term in the first law of black hole thermodynamics. So now if you had the standard differential for the internal energy, as you are used to from your course on thermodynamics, you would have minus PDV term. So however, here you are getting plus VDP term. So what that means is that the mass on the left-hand side cannot be interpreted as internal energy, but rather it's a different kind of energy. It's a gravitational enthalpy. So that was all identified in this paper, and basically the difference between the energy and enthalpy is precisely this one. But the physical meaning is that basically the enthalpy is an energy to create a system and put it in the environment. So we are actually creating a black hole and putting it in the environment of the cosmological constant.
Can I ask one question? How did they derive this? I mean, did they take explicit solutions and then vary parameters and then derive that they? Or is this something that this identity something that happens in solution space, or is it something more like a?
They use the general Hamiltonian perturbation theory, I think. So it should be quite general. So they started with a space-time which didn't even So it should be a general proof.
Yeah, but maybe because that this is a first law, and then there's what people usually refer to as two different ways or different versions of the first law. One of them is the equilibrium state first law, where you're moving from one solution to a nearby solution, equilibrium solution. And then there's the physical process first law. I imagine that it was the
first law,
stationary, the stationary version of the first law, right?
That's correct. Yeah. I mean, it's certainly once you start varying the cosmological constant, you basically vary the theory, and I think it's very difficult to interpret that as a physical process, which would be happening.
Well, I mean, there's the Teitel-Bohm-Brown mechanism of nucleating brains, or absorbing brains, or annihilating brains, right? That's the most physical thing that.
I agree. Yeah. So you're actually trying to defend my thing. That's amazing.
Yeah. Okay.
Sorry, can I ask another question? Is this supposed to be valid for planar black holes in ADS?
It should be valid for any type of black holes. Of course, we were mostly in this talk. I will be mostly concerned with spherical black holes, but the planar black holes are, it should be valid for them as well. Yeah.
So, well, I'm asking because that case, at least for me, is a little clearer conceptually. So, this gravity theory in ADS supposedly has some dual gauge theory. And is this pressure then supposed to be the space-space component of the stress tensor in the dual gauge theory or not?
I don't think so. So I will try to explain what I think the corresponding dictionary is at this point. But no, this is simply the bulk pressure of the cosmological constant.
Yeah.
At this point.
So this pressure is not
not necessary.
Okay, so normally we identify, the symbols that you wrote down, like entropy and temperature and so on. We identify the thermodynamics in the bulk with the thermodynamics in the gauge theory. And those symbols actually have a double meaning because they mean entropy in the bulk and entropy in the gauge theory. So you're saying for pressure, that's not the case.
That's precisely right. And then, don't worry, wait a couple of slides, and then I will try to, give you the dictionary, which as we understand it now. But you are precisely right. There won't be identification between the VDP term here in the bulk and the corresponding VDP term on the boundary. It will be something different.
So then what do you mean by V?
Okay, so here I simply take this first law, if you want, as a definition of V. So I would define whatever this conjugate quantity V is simply as dm over dp, where I keep all the other quantities constant, right? So I define it with this thermodynamic first law. So there are some independent geometric, definitions of V, and they sometimes agree with this V and sometimes they don't. But at this point, I think the clearest way is to simply define whatever needs to be here. Is here, and it's defined by this first law. And then the question is, what is the meaning of this quantity V? Certainly, it is some kind of volume. It must be. But what is the meaning of that volume is very interesting.
Okay, so it's not, there's no obvious geometric interpretation of this volume as as a real volume in the bulk.
Yeah, as I said, so there are several geometric definitions of this volume, and in simple cases, they indeed coincide with this V. But the best thing we have in the bulk is whatever is on this next page. So let me go to that next page, and hopefully that will answer that question. So exactly. So we have this volume, and we define it as dm over dp at other constant quantities. And then when you actually use it for Schwarzschild ADS, what comes out is this 4/3 pi r horizon cube. So it's a very amusing formula. It looks like the Schwarzschild solution is actually a ball of radius r plus in the Euclidean space, right? But
sorry, David, to keep interrupting you. So
yeah, that's fine.
For planar black holes, would this V be infinite or finite? Would you get the same formula or?
I mean, yeah, you need to consider something like a volume per area or something like that. I think it would be infinite. I think,
but in that case, it would be. I mean, that's I mean, relative to what you said before. The volume that you talked about before is the volume in the gauge theory, which has different dimensions than this one. And David, when you were talking about the planar blackboards, in that case, you can define a volume, but that's the volume in the gauge theory that has one less dimension than this volume. And the pressure is a completely different thing. So, I mean, for a planar blackboard, we can have a PdV term that refers to the volume of the gauge theory. I mean, you take your planar gauge theory, you put it in some with periodic boundary conditions, so you have finite volume, and then you can consider variations in this. That volume for a four-dimensional bulk, that would be a two-dimensional volume.
Yep.
Whereas this one is three-dimensional. So they are different, very different objects.
Yeah, that's why I was trying to understand. So this is a volume of something in the bulk.
Yes.
Okay.
And you can basically understand it as a sort of volume hiding behind the black hole horizon, but it's very, very naively, right? So it's something. Yeah, the interpretation is. So anyway, so we are trying to understand what this volume is, and for Schwarzschild ADS, it gives you this very nice simple formula. However, if you have, let's say, already rotating black hole, then this is not so intuitive, and you pick up some extra terms which don't have necessarily geometric meaning. And so what we were thinking, and then in the end, with Gary Gibbons and Miriam Svetic, we came up with this proposal of reverse isoperimetric inequality. And so basically, isoperimetric inequality is something which relates the surface areas to the volumes. And so typically, if you have some body of some surface area and then some volume, then it satisfies the volume, and the area satisfies some kind. You form a dimensionless ratio out of them, and then this has to satisfy certain features. And of course, let's see, what is it? The volume is maximized for the sphere or minimized. I never remember, but one of those. Okay. And so for the other ones, it's always, the inequality is not equal. So now, we were looking at a bunch of examples for this volume, and then we came up with the same. This is the isoperimetric ratio. So you take the volume, you take it to the right power so that the result has dimensions of length. So this is the area of the sphere. And then you take the area, and again, you form the corresponding, length out of that. And so this is a dimensionless ratio. And so the conjecture was, at least what we have seen for various black holes, is that this R is bigger or equal than 1, and it's equal if and only if you have spherical black holes. So you have Schwarzschild and stuff like that, non-rotating ones. So then we formulated, like, for black holes of given thermodynamic volume, the entropy is maximized for Schwarzschild ADS. So that was, the only interpretation of this quantity V which we, sort of could come up with. But it's something which you would expect from the volume to be true. Okay, so that's some kind of inequality which is satisfied here. All right. So now what is really, from a pragmatic point of view, what is interesting about these things is that now you get a consistent smart relation in ADS space. And the reason is that if you have the first law, where the VDP term is varied, and then you use the dimensional analysis on this one, and you use the Euler scaling argument, which I can review if you are interested in later, then actually you realize that you need this extra PV term in the smart relation. Okay, so if you don't vary VDP here, then you wouldn't expect this term to be present for the smart relation. And of course, then this wouldn't be true. So the statement is that if you want a consistent smart relation for ADS black holes, for consistency, you need to vary the pressure in the first law so that these two are consistent. So that's a pragmatic point of view why you should vary the cosmological constant. Okay, so another consequence of having playing with this VDP theorem is that you can discover various phase transitions, some of which were uncovered before the black hole chemistry was discovered, but some of which actually were only discovered later on. And of course, ADS black holes have nice property that they can be in thermal equilibrium, and they exhibit interesting phase transitions, and they somehow should correspond to the CFT phase transitions on the boundary. So in this talk, I will just discuss the canonical ensemble, the simplest one, which Roberto already came up with more than 20 years ago. And that's sort of like van der Waals behavior of charge ADS black holes. So let's just consider the simplest four-dimensional charge ADS black hole. So this is it, Reisner-Nordström ADS. And so here are the standard thermodynamic quantities, except the volume. The volume again, the charge doesn't, the U1 charge does not change the volume. So this is still 4/3 pi r cube. And then let's just consider the standard free energy, which is m minus Ts. Okay, so then, the statement is that already these, very simple charge ADS black holes behave sort of like van der Waals fluid. So let me just recollect what van der Waals fluid is. So here's the van der Waals equation characterized by two parameters A and B. This is the specific volume, the pressure, and the temperature. And so we know that, if we draw the isotherms in the PV plane, then for sufficiently high temperatures, this is boring. It just goes up here. But at some temperature, we develop an inflection point, which corresponds to the critical point. And then below that, we see this oscillatory behavior. And of course, the oscillatory behavior is unphysical. We have to use the Maxwell's equal area law to actually, describe the transition between liquid and gas over here. Okay, so what is very interesting is that the critical point, for the inflection point is characterized by this critical ratio 3/8, which is PCVC over TC. All right, so now here comes the version 1 black hole criticality in the phi q plane, which is due to Roberto in 1999, and also other people over here. And so what Roberto actually noticed is that if we take the charge ADS black hole and then plot the isotherms in the phi q plane, then we see similar behavior. So this is for large beta, beta is 1/t. So for large beta, we see something like that, but at certain critical beta, we see an inflection point. And then for smaller beta, we see sort of oscillatory behavior. And in the vicinity of the inflection point, there will be a Maxwell equal area law. So what that means is that there will be, again, a critical point. There will be some first order phase transitions below that. And so what Roberto basically proposed is this analogy with the van der Waals fluid. So whereas on the fluid, we will have like temperature, this would correspond to 1/temperature in the ADS black hole case. And then the pressure of the fluid will correspond to the charge, and the volume of the fluid will correspond to the electrostatic potential. So now if you plot the free energy, then it characterizes again, above the critical charge, there's just boring behavior. But at critical charge, you develop this inflection, well, not inflection, but the cusp here. And then below that, you see like the characteristic swallowtail, which corresponds precisely to these first order phase transitions. So now what's really changing here is that if you start here, you have small black holes, and then you should be minimizing the free energy. So you don't always go to full swallowtail here, but you rather jump to the lower free energy. And so there will be a first order phase transition at this point here of the swallowtail, and there will be a first order phase transition between large and small black holes. All right, so this is the analogy which was discovered already, as I said, 20 years ago, and it's in the phi q plane of the charged ADS black holes. Okay, so now what we did 10 years later or something like that is that we said, okay, let's look at this like with the same bulk quantities as you expect for the fluid. So let's now, this is again the van der Waals fluid equation. So now let's identify this P really with the bulk pressure of the cosmological constant, and this V with the volume of the black hole, and this with the temperature of the black hole. So instead of the van der Waals fluid, we now have something like this. And then you see that it's not precisely van der Waals equation, but it's something which qualitatively behaves very similar to the van der Waals equation. And you again have the Maxwell equal area law, and there will be a phase order first order phase transition between small and large black holes. So now if you compare how the free energies look like, so this is for the standard van der Waals fluid, you see the swallowtail here and how it looks like. Here it's for the charged ADS black holes. So now, what we are really doing is that we are comparing, we are plotting these things as a function of temperature for a given pressure. So if we are above critical pressure, everything is boring and no first order phase transition. If you are below the critical pressure, we develop the swallowtail. And this is it. So now you can plot the phase diagrams, and you see that for the van der Waals fluid, it's really, really similar to the ADS black holes. So now you can look at the critical point where the phase transition is of the second order, and you will see that both cases are described by mean field theory critical exponents. So they are of the same universality class. People also were concerned about the slope of this equation, and it's again very, very similar. Of course, that's described by this equation over here. Yeah, but it sort of like completes the analogy between the van der Waals fluid and charged ADS black holes, right? So it was like completing what's happening in the bulk with the van der Waals fluid. So now I think this started the golden era of black hole chemistry, and then people started looking at more and more complicated black holes, and then they started discovering more and more interesting phase transitions similar to this one. So for example, if you went, I don't know, this is probably, I don't know, rotating black holes in 5-6 dimensions, I don't remember, is that you recover something like, solid liquid gas phase transition almost. What you really recover is, 2 critical points here. So this one is not going to infinity, but it terminates at a critical point. And then, you have a triple point in the middle, as you would have in this thing. So now I think the most interesting for Roberto maybe is this one here, because at some point we discussed this, and then Roberto told me, well, I don't think general relativity can ever go beyond mean field theory critical exponents. So Roberto told me, well, you will always discover mean field theory critical exponent for any critical point. But I don't know if you've seen ever this in normal thermodynamics. What we discovered is basically you can have this isolated critical point where you have sort of one swallowtail merging to another swallowtail. So you have like sort of 2 swallowtails which are separated, and then as you move the parameters of of the space-time, these swallowtails go closer together, and at some point they merge. And so if you look at this point over here, that's not described by mean field theory critical exponents. But probably that's not what you meant, Roberto, right?
Yeah, what I had in mind is something that would be irrational exponents, and that's if you have a smooth geometries, then that's I don't know how you can get them. I mean, you can get them out of singularities, but not out of smooth horizons. But I mean, this is a phenomenon that I certainly didn't expect or anticipate, this merging of swallowtails, yes, or collision of swallowtails, yes. Yeah. Which is, I think that's interesting, yes.
And let me highlight here that Antonia played the main role in discovering this thing here. Okay. All right. So then there were other phase transitions discovered, and people even define something like superfluid phase transitions. And even more recently, people even try to play with whether they can define other critical exponents. And one proposal, which is over here due to Robman and these people, is that basically they were looking at the thermodynamic geometry of the corresponding the corresponding thermodynamic geometry. And of course, at the critical points, typically, the curvature, or there are singularities of the corresponding thermodynamic geometry. And so this is the corresponding, I think, Ricci scalar for the thermodynamic geometry. And so what they propose is that this diverges at the critical point, but maybe they can extract the divergence and they can define this critical exponent nu over here. And that was also mean field. So I would say that this is sort of like golden era of black hole chemistry, where you really try to map whatever is happening on the black hole side to whatever is happening in the standard thermodynamics of normal fluids and stuff like that, and you're comparing the same type of quantities, pressure to pressure, volume to volume, and so on, and you are discovering that most of these things are actually behaving like this, the standard mean field theory critical exponents, and you discover some other interesting phase transitions and so on. So, we have very rich structure of phase transitions.
Can I, since you mentioned this thermodynamic geometry, it's something that I've seen over the years. To me, thermodynamic geometry has always been some sort of fancy, if you want, elegant rephrasing of just usual thermodynamic relations. And I don't know what to, and are you saying that here there's something more than this, and that we can get some physics out of thermodynamic geometry that we couldn't get otherwise? Because it's something that I'm just asking for your kind of honest opinion. I gave you mine, which is...
I personally am very skeptical.
Okay.
And especially if you look at this paper, it's just like they do it for two-dimensional metrics, but for two-dimensional metrics, R is always 0 or something like that. So they do some, some weird thing. Yeah. Okay. So I'm very skeptical, but certainly, what they got by this definition is that they got the standard mu out of that. Okay. But I wouldn't. I wouldn't bet my life on that. Okay, very good. So so that's the golden age of black hole chemistry. Everything works nicely in the bulk. But then the question is, of course, and that's been bothering people for some time. What is the interpretation on the dual CFT side? What is the interpretation of this VDP term on the dual CFT side? Very good. So let's now move here. And so there's a couple of proposals here. But basically, what the main theme is that you can show that this ADS radius somehow proportional to the number of colors of the dual CFT, and so already in these papers here, which are quite now old, people were saying, well, okay, so what really is happening is that VDP term in the bulk does not correspond to VDP term on the boundary, but rather is some kind of chemical potential term where you have the chemical potential for number of colors of your dual CFT. All right, so that was basically the proposal which people demonstrated on a couple of examples, and this was the state until, let's say, 2014. And then this paper came out by Clark and Robinson, and then this year a new paper came out. And so what, of course, was not satisfactory completely is that the ADS radius not only determines the number of colors here, but it also determines sort of the volume of the CFT where the CFT lives, right? So in principle, the CFT lives. So again, I am interested in the spherical case. So the CFT lives on some radius, which is defined over here, and typically people take this radius to be the ADS radius. So that would be the thing. Of course, how this comes out is that this is the asymptotic behavior of our ADS metric, and then what people do is that they multiply this by arbitrary conformal factor. So let's use the conformal factor R, capital R over R. And then we have the metric over here. So now the standard choice is to choose the radius for the CFT to be L, in which case I'll just have minus dt square, and then I'll have L squared d omega square here. And then the volume of the CFT will be, L d minus 1 omega here. But, it's especially Manus is pushing for the ideas that we don't have to do that. Right, we can put the CFT on any radius if you want, and that of course will partly modify the standard dictionary, as you will see a little bit later. Okay, so basically we have two options. Either we choose R equal to L, so this is our volume of the CFT, and of course then it's obvious that as we vary the cosmological constant in the bulk, not only the central charge changes of the CFT, but also the volume of the CFT changes because L changes. Yeah.
Can I make a comment here? So I mentioned this to Matt, who gave a talk recently here.
Manus.
Sorry, Matt. My apologies.
It's the other wizard. Yes.
Yes. Sorry. That was let's not call that a Freudian slip. So if you were doing holography in a case where you really understand, let's say n equals 4 super Young-Mills and ADS 5 crosses 5, then the radius of ADS is not dual to the number of colors. It's dual to the tooth coupling. Because you have two parameters, the number of colors and the tooth coupling. So at least in that case, which I think I understand better.
No, but can I interrupt? So, I mean, the radius measured in Planck units or the radius measured in string units, right?
Yes. So if you do the duality with string theory, not with gravity, because it's not a duality. So this is a duality between a gauge theory that has two parameters and a theory in the bulk that also has two parameters. Okay, alpha prime and L Planck if you want, or the radius and N and the 5-form flux, whatever, you can parameterize it in different ways. But it seems to me that when people play this game, because they restrict their attention to ADS5, they conflate the two parameters into one. And then the radius of ADS ends up being dual to the number of colors, when in fact there's also another parameter.
That's a choice, isn't it? And what I think it's
if you have a top-down model, it's not a choice. There's a correspondence between parameters. No.
When you have to specify what are the basic parameters in your quantum gravity theory, and you can say that it's a.
That's why, Roberto, I'm saying let's look at a case where I think there's a precise, or at least as precise as it gets, dictionary. Right, and in that case, if you want to change the number of colors, what you need to change is the 5-form flux, not the radius.
I still think it's a choice.
I'm just asking for your take on this, David, because I mentioned it to the people, and I guess different people have different opinions about this, like you can see with Roberto.
Yeah. So, I think actually, it's precisely these people are looking at the standard case, ADS5 process 5, I think. And so they still had the conclusion like that. So I don't know.
Yes, but in that case, I would change. I am very sympathetic to thinking of changing. Well, I get confused because I would say that changing N, changing N is really the quantized flux of the 5-form. So, and then that's why if that's what you do, then I'm very sympathetic to thinking about a chemical potential for that and seeing where that takes you. With the cosmological constant, I get a bit more confused. I just wanted to know your opinion on this.
Yeah, well, I don't have any opinion. So, yeah.
Okay,
Yeah, I'll think about it. So anyway, so Manus was saying, well, okay, so let's not do that. Let's not choose R equal to L, and let's just keep R completely general. And so if you do that, then of course, this volume here is independent of the variations of the cosmological constant. And so in that sense, everything that's happening in the bulk would be actually corresponding to what was happening in the central charge. Okay. So anyway, so this is the first law Manus has proposed this year. And so you see, well, proposed, sort of derived. So you see, you have the standard terms on the CFT side, but you have these two weird terms. One of them is the minus PdV, where this is the volume of the CFT. And then the other one is precisely that is the chemical potential times delta of the central charge.
Can I, before you go on, because I don't want to get lost, okay? I don't want to get confused. So you're saying here that the PdV term, that's the V is the volume of the CFT.
Yes.
Which is not what we had before.
That's right. That's right.
So then the volume
is this V here.
Yes. So in the planar case, that would be the volume. I mean, if you of the torus, where you put your theory, right? And that's a term that we understand well in conventional terms. The one that's different is the last term, mu dc, right? Okay, that's. I mean, it's just that I want to make sure that I'm not mixing things up while trying to follow.
Yeah. So one thing which is to be noticed here is that contrary to whatever is happening in the bulk, where we have plus VdP, you have here minus PdV. So really E here is the internal energy. of the CFT. It's not an enthalpy anymore, it's the internal energy. So then, you know, that's very interesting, because you are saying it's the same mass, right? It's the same mass, but you have two different interpretations. On the CFT side, it seems like it's behaving like an internal energy, whereas on the bulk side, it seems like it's an enthalpy, right? So sort of it makes sense, like for, you know, you don't really have cosmological constant on the CFT side. So I would say that it doesn't make sense to put it like in the environment where there's no environment. So it's, you hardly can distinguish the two there. But anyway, it's interesting. So now what these quantities mean is that your first law is accompanied by two smart relations. So one of them comes from the dimensional analysis, and it's known as the equation of state, which is this one here. So really, you look at the dimensional scaling of all these quantities, and you recover that basically this pressure or whatever is given by this formula here, the CFT formula. And the other one comes from, you know, how things behave extensively with the central charge. And so because the volume does not behave extensively with the center charge, the PV term does not appear here. So the first one is known as the equation of state. The other one is known as the holographic smart relation. So now what is very, very interesting, again, when you think about the ADS, you know, bulk thermodynamics, is that I shown you some smart relation there, which was consistent with the first law. But that one had d-dimensional factors here. So it had some like d-2 over d-3 and stuff like that. So this does not happen on the CFT side. So here you really get the standard, like the Gibbs-Duhem relation here, but in the bulk you don't. So anyway, so this is what's happening on the CFT side. And then, of course, you can go back to the bulk. And because I have chosen this radius r, you know, the standard formulas get a little bit reshuffled by choosing, you know, putting the CFT on radius r. So you know, of course, if you don't like that, you can put always r equal to L, and E will be equal to M, and so on. But and then this is the corresponding dictionary. And so what I am taking here for the dictionary of the central charge is I relate it to the ADS radius like that, and to the Newton constant like that over here. And that will be true in the Einstein gravity, where, you know, the standard central charges all coincide. All right. So now once you do that, you get from your CFT first law, you get the following bulk first law, where now actually, because you vary two terms on the CFT side, you also will have two variations of you know, extra quantities on the bulk side. So now you have to vary both lambda and g Newton. Okay. Yeah.
You now introduce a variation G Newton. Was that before, or
no?
I don't know.
No.
Okay.
So this is
no, because I mean, it's something that if you're going to, I mean, you introduce it, you pulled it out of.
Yeah. So that basically comes from here. Okay. So look, I have two terms here which vary in addition to standard terms. Okay, and so let's say in the standard case where the volume V is given by the cosmological radius. So you know, if I want to vary V, I have to vary lambda, right?
Yeah.
So now, in order this term not to be sort of like dependent, if I am to treat this term as independent, I also have to vary the other term. I also have to vary the Newton's constant. And so this is precisely what's being done here. Okay, so suddenly you have the first law which has, you know, variations of both, of lambda and g Newton as well. And of course, you know, you can do that, but you don't have to do that if you still keep your CFT on this capital radius r, then varying V just corresponds to varying of this, you know, capital R radius of the CFT. And in which case you can still only vary one of the two, either dg or d lambda, to have two independent terms.
So can I ask something? Where you have G Newton in all of these expressions depends a lot on how you define each term, because you can shuffle it around, and then you're going to get different things depending on what. Because I mean, you here you have a lambda, but in order to transform it into some other I mean, you can transform it in some other quantity that also has a G Newton, and then you may say maybe that's going to be, I don't know, the pressure or whatever. So what's your choices here for where you have, because G Newton, if you want, at the end of the day, you can always, at the classical level, pull it out of, or push it out of your action, and then it's going to be nowhere but in an overall factor of everything. That depends on how you define your physical quantities. G Newton is a conversion factor.
Yeah, so
it's something that they use to convert lengths, which is what you have in a geometric theory like a GR, and then you convert other quantities, I mean lengths, into, well, other quantities that may be masses, they may be temperatures, they may be whatever you want. So it's a conversion factor, and then getting physics out of a bar in a conversion factor, that's something that makes me a little uneasy.
Yeah. Okay, so first of all, I agree with you that yeah, you can put G Newton anywhere you want, and it also depends on how you define your action and stuff like that. Yes. Right? And so we had a big discussion, because in your paper, Roberto, you put G Newton in front of the whole action. So of course, I'm used to more the writing the Einstein equations as G mu nu equals to 8 pi G T mu nu, where really the G describes the coupling to the matter and stuff like that. So in which case you have in front of half of the action, but not in front of the other half of the action.
Yeah. I mean, you can choose. I mean, that's something that, I mean, you choose it at your convenience. As I say, it's something that you use in order to relate energies to lengths. That's
and by any means, I don't claim that this is, that if you have different conventions, of course, this first law will look slightly differently, and I agree with that.
Yes.
Yeah. But I mean, the most important thing is that, once you fix your conventions, I think you will get a unique first law.
Yeah, of course, once you fix things, but what you get exactly will depend. I mean, here you're writing this in terms of area and surface gravity, for instance. If you did it in terms of entropy and temperature.
Yeah. Definitely. And I will show you another first law, don't worry, where I make a different choice, okay? But you have to really think. I think you have to be specific of what you want to study, and what are your conventions, and then I think it sort of comes out uniquely. But yeah.
Okay.
All right. So that's the corresponding bulk first law. Very good. So just to take away, we can do things which are consistent with the CFT, but you pick up two non-standard terms on the CFT side, minus PdV and mu dc term, or on the bulk side you get d lambda and d G Newton, or some variations of that. Okay, so that's the takeaway home message. Very good. So I don't know if I should speed up or not. So let's first look at the CFT side, and so I'll be very brief here. So this is our first law. And then we look at, again, our favorite charge radius black hole. And then you have so many ensembles to consider, right? You have two to the three ensembles, which are sort of interesting. And then you can easily show that actually 5 of them are not interesting. So if you write it in terms of these variables, it's not interesting. And these 3 ensembles actually are interesting, sort of. So the most interesting one leads to version 3.0 of the van der Waals behavior. And that's the mu c criticality. So you look at the ensemble where you have as variables Q, V, and C. So this is the V of the CFT and the C of the CFT. And then you can plot it, what happens as you vary Q, which is basically what Roberto was doing many years ago, except that you didn't have the mu dc term. And then, however, now what we can do is that we can also, fix Q and then vary C, and then you get a very similar picture. So this thing here is plotted for various C's, and then what you will find is that if the central charge is small, then nothing interesting is happening. That's this blue curve over here. And then if it's critical, you get this kink, and then if it's large, you get a first order phase transition. So only basically CFTs with large central charge will have this interesting phase transition. And so let's describe it over here. So that's the corresponding phase diagram. And so what we are plotting is not C, but 1 over C for some reason. And so this is the critical central charge over here, and that depends on the charge of the black hole. Okay, and so what is not surprising? So remember that this is an ensemble where I keep the volume of the CFT V fixed. Okay, so all these pictures are here for fixed volume. But if you started, varying the volume, it wouldn't have any quantitative or effect. So the only thing is that if I vary volume over here, then just this critical point would move left or right a little bit. But whether there is a first order phase transition or not really depends only on the value of C, on the value of the central charge.
Can I interrupt you once again?
Course,
it doesn't matter. Yeah, you don't have to rush because we're interrupting you a lot. It's something that you mentioned before, but I want to. So here you're putting fixed in quotes, and the way that I see it is that, of course, in a conformal field theory, fixing the volume doesn't really make sense because you can change volume and the theory doesn't change. You can change all scales, right? So how should we understand these changes? That you get something out of changing the volume here.
Yeah, precisely. I'm saying that it doesn't matter, right? So yeah.
Okay.
Yeah, that's precisely what I'm saying.
Okay.
Yeah.
No, sorry,
so
if you have other scales.
If you have other scales, yes.
Potential or temperature, things like this.
Yes.
The volume relative to those scales is physical.
Yes, in that case, yes. But I think that and that's not here. I don't know. Maybe I'm just confused about what is going on here.
So what I'm saying is that. So let's see. I wanted to explain this in the bulk, but let's do it here. So I plot this free energy here as a function of temperature, right? And so then I choose, let's say, one concrete C. Let's say it's the one which is the green one, right? So then you may be asking, what would happen if I start changing the volume here? So now I start plotting these diagrams for different volumes. So the answer is the qualitative shape of this curve does not change. It will move a little bit down or whatever, but it will still be the swallowtail for any volume whatsoever, right? So for that given central charge, you simply have first order phase transition for any volume of the CFT. Okay, so then I can choose a different central charge, let's say the blue one here. So then I don't see anything interesting. But again, if I start changing the volume, it will start shifting a little bit. But again, it will not have any qualitative, difference. It will still remain boring, and there will never ever be first order phase transition. So in that sense, the volume does not matter. But I agree with David that we have the temperature and other things, so it's really like part of CFT. But
you're always. What I think what you mentioned is that you always vary the volume relative to some other scale. But here, are you varying just the volume, or are you, because what you vary if you perform a conformal transformation, you vary the volume, but you also vary the normalization of the time of time, and that varies the temperature, and that's essentially what we're saying, right? That if you vary the volume, that you vary in the same in a compensating way the temperature. But here, are you performing a variation of just the volume without varying the normalization of time?
So you're basically asking about this thing here, right? So basically, varying the volume corresponds to varying the R, but that corresponds to varying everything, right?
Everything,
temperature, and
everything. Yeah. So it's variation of the volume and variation of energy scales or the energy units.
Yeah.
Okay.
So then this is sort of So this is what I mean by that. Okay, so I think I am running out of time, so let's not discuss. There's another interesting ensemble, which is very interesting from the fact that we don't understand why it's happening and what's happening. But if you just look at whatever it's this ensemble here, but if you look at what is really strange about it, and if you look at this phase diagram sort of here, then you see that the temperature goes here and it's increasing, but somehow the high entropy state is stable at small temperatures. So at small temperatures, you have high entropy state, and at large temperatures, you have low entropy state, which is something which is very counterintuitive to, at least to me. And maybe we can discuss this example any further after the seminar. But it's something very, very puzzling, and maybe it has simple explanation, but it's just from the first sight it looks very puzzling. Anyway, so let's go to the bulk. So now we have the full bulk first law, which is this one here, which I showed you before, and then yeah, it depends how you organize the G's. I agree with that. So very good. So in black hole chemistry, we only varied lambda and held G fixed. And then that corresponded to varying the central charge, but also the CFT volume, at least in the case when capital R was equal to L. And then what was really interesting is that really we could identify the thermodynamic quantities with the thermodynamic quantities of the fluids, and really the cosmological constant was the control parameter which controlled, well, if I increase the pressure, there will be a first order phase transition. If I decrease the pressure, it will just be all boring and smooth and stuff like that. So changing the cosmological constant, changing the pressure, really corresponded to whether what the system is doing, right? So now we have the variation of G as well. Okay, so then the question is, what happens for this black hole chemistry, for these results over here? And then, of course, as you may already expect, from what I've shown you, you will see that basically the changing of the pressure will not matter. Okay, so how to see that is that we propose this very crazy mixed first law, which is a different organization which of the quantities of G's as Roberto wanted. So very good. So this is our formula for C. We just differentiate the formula, and we come up with the new formula, which is partly bulk and partly CFT, right? And so this is really the pressure P, which however now have the cosmological constant varied in it as well. And this is the central charge, and this is the corresponding conjugate quantity. So now this VC and this mu is different from what we have seen before, right? But what this ensemble, it's crazy ensemble. It's sort of like half bulk, half CFT. I was trying to convince people that maybe one can understand it as a bulk first law, but I'm not sure. But I was trying to argue that the C sort of could be understood as an asymptotic charge for the bulk, but maybe not. I don't know. So if you understand it as a flux or something, then maybe anyway. So what this allows you to do is really to study what's happening in the bulk. Let's say as I vary pressure, but I can, for example, fix the center charge. Okay, so I fix the center charge and I study with what's happening over here. And then, as you may expect already from the CFT side, this is again, leads to interesting behavior. But again, the behavior is completely independent of the pressure. So what I change here to get again our favorite swallowtails or not swallowtails only depends on the value of the central charge. Again, if you fix the value of the central charge, let's say the one with the green one, and start changing the bulk pressure, then again, you qualitatively get very similar curves as the green curve. So what it shows is that P does not really matter. The bulk pressure no longer matters. So you really definitely lose the nice interpretation of the PDV term in the bulk once you consider the central charge variations and so on. And it's the C which is the control parameter. Sorry. Yeah.
So you're fixing G Newton, and what else? I mean, you had it in your previous slide.
So
while both. Oh no, okay. So you fix the central charge, and then you let G and what's the other thing? I. What's I?
L.
L.
Sometimes I put small L, sometimes put the big L. So the idea is so you vary the cosmological constant. You vary the G Newton constant,
and you keep the central charge
and
fixed.
you keep the central charge fixed. Yeah. Yeah.
So that's I mean, putting it in stringy terms, because I mean that's so you're varying at the end of the day the Planck length and the ADS radius, keeping the ratio fixed.
That's right. Yeah. So these processes sort of should correspond to fixed CFT theory. The
Yes.
CFT theory will be changing the volume if you want. Yeah. But I do it in such a way that the central charge is fixed, and of course that leads to varying G, varying lambda in the bulk. But it's in this very specific way. It's like really trying to approach the black hole chemistry as close as I can, right? So I want to sort of be able to vary P, but at the same time, yeah.
But then this conclusion that you don't get that the PV term doesn't matter, is that surprising after you've done this, or?
If you if you know the CFT side, so remember on the CFT side, well, we did it the other way around, right? But what I mentioned from the CFT side is that the V does not matter, right? But it was the CFTV, but the CFTV is sort of lambda, right? So the lambda should not matter, and if lambda in the bulk sort of corresponds to the bulk pressure, so P should not matter, right, in the bulk. Right, so in that sense, it's not completely surprising, but it's surprising from the point of view of the black hole chemistry, where really P was the control parameter. Right. So yeah. So anyway, so this is what happens, right? So you get phase diagrams again. The critical the critical point only depends on the value of the central charge. So if it happens for given Q, it happens for certain value of the critical charge. If you are above, there is nothing interesting. If you are below, you have first order phase transitions and varying pressure. The bulk pressure only corresponds to qualitatively moving these things. So again, the same conclusion as on the CFT side is, if you have when you have large number of degrees of freedom of the CFT, then you can have a phase transition, and the pressure no longer matters as it did in the standard black hole chemistry. Okay.
So this is large in the sense of being larger than this critical.
Than the critical value.
Not in the usual large sense, but here n is large, but it has to be larger than some critical value, right?
Yeah, exactly. Yeah. And it's given over here, and k is just a constant, which is not. Yeah. Okay, so I mean, this is all very puzzling to me. So there are also alternative proposals, like why don't we started as varying lambda, and we didn't like varying G, so now we like to vary both, right? So why can't we vary actually just G and not lambda? And that's the proposal over here. Okay. Of course, maybe the right thing is not to vary G and not to vary lambda, right?
Well, varying G and varying, I think that they are very different things, right? Because lambda is some parameter that appears in your theory. G, as I say, it's something that you can think of it as either just specifying what's the Planck length, and then that's just fixing some reference scale, or otherwise it's otherwise it's just as I was saying, a conversion factor. And then it depends on, I mean, how it enters, it depends on how you define the other quantities. As I say, if you write this first law in terms of area and surface gravity, then your factors of G Newton enter differently than if you write it in terms of T and ds, right? As we were saying before. And this happens with, I mean, that's the most important term where this appears, but you can do the same thing with essentially everything else. I mean, so varying G Newton is something that I see as varying lambda. I can understand, at least from the formal point of view. I mean, what you're doing. The other thing, I think it's much more, to me, I mean, varying G Newton, it's something that's,
I see,
less well justified.
Yeah. So anyway, so these are the recent proposals where they just vary basically G Newton, and of course that doesn't matter on whether you are in ADS or not. So they just do it in asymptotically flat space and so on. So anyway, so let me summarize this very complicated story, right? So there is something which is called this black hole chemistry, and it was the standard thermodynamics was developing like last 10 years, and it was like really I fix G and I vary cosmological constant. I interpret its variations as the bulk pressure, I pick up this VDP term in the bulk, and then this volume here sort of has a meaning of the volume of the black hole, whatever that means. So now, this has benefits that you now have a consistent smart relation with this first law. It has a interesting feature that M is no longer an energy, but it's a different kind of energy. It's enthalpy. And then, of course, this leads to by studying different values of the pressure, people discovered, new phase transitions, which people haven't noticed before because they studied at fixed lambda. And, for some lambda, you don't have these phase transitions. And, as an example is this one, the Waals criticality, which really corresponds to whatever happening for the fluid to whatever is happening to the black hole. However, there was this, interpretation of the CFT side, and, people like Kark and these people, they argued, well, it's very strange, right? So I vary lambda in the bulk, but it corresponds to varying both the central charge and the volume of the CFT. So there's like not one-to-one correspondence, right? And so then, Manus, came up with this extended first law where you have two terms here, and that translates to varying both G and lambda in the bulk. And so this was the complication that I can put this thing on a completely different radius than ADS radius, and then I can just vary one, let's say lambda. And so then I am back to the standard interpretation. So I thought maybe I like this one the most, but anyway, it's just a matter of taste. Okay, so then what we have done in the last part is that we said, okay, very good. So now let's return back to the bulk and with variable G and lambda, and let's write it in this mixed first law where I can actually keep the central charge fixed. And so I am getting as close to black hole chemistry as I can. But suddenly the betrayal is that really the pressure is no longer a control parameter, nothing happening new when you start changing pressure. It's really when you start changing the central charge. It's the value of the central charge, which is important. And so, of course, then you sort of have like mu C criticality instead of PV criticality. But of course, that's very hard to map to van der Waals fluid, where you have PV criticality for van der Waals fluid. So it seems like the direct comparison to fluids with the PV thing is lost. And so I call that the fall of the black hole chemistry. But Rob, of course, disagrees. So here are some open questions.
David, can I make a comment?
Yep.
So this independence of the pressure that you mentioned of the thermodynamics reminds me of what happens if you have confining geometry. You can turn on a chemical potential, but the physics is completely independent of the chemical potential because you don't induce any charge. Simply because the flux lines wouldn't have anywhere to go. So, but that's only true because it's a large N effect. It's also the same if you think about the dependence of for example, the free energy of a confining geometry. It's independent of the temperature. Okay, simply up to the confining temperature, because you don't have a horizon. So at order n squared, the entropy is 0. It doesn't depend on the temperature. You would only see it if you computed the loop. It would be order n to the 0 or the 1.
Okay.
So I'm just saying that this fact that you find that thermodynamics does not depend on one of your control parameters is not unheard of.
You said that so in the case of charge, just that would stop being the case if you include 1/n corrections. Is that because of percreation?
It's because well, sorry, I should be more precise.
Because what you say is right, that you don't
sorry. You need to go, I think, thank you, Roberto. You need to go to a chemical potential of order the lightest charged carrier so that you can nucleate it.
Okay.
Yes, like in QCD, for example, that would be the mass of the proton.
Okay.
If you turn on baryon chemical potential.
Okay.
And also, the chemical potential is also an intensive control parameter, just like the pressure. So I don't know if there's an analogy there.
Oh, that looks very interesting. Yeah, yeah, because that's what we are seeing here, right?
Yeah.
Sort of. Yeah. Yeah, unfortunately, in our case, it's precisely the control parameter which we like the most, right? But
Yeah.
All right, so here are some open questions for you. So, I think it's not a problem at all, but some people seem puzzled that m, the same quantity m, is interpreted as enthalpy in the bulk and as an energy on the boundary. I think it's not a problem because on the boundary you don't have lambda, but yeah, but you still have the pressure and the volume there. So I don't know if this is really a problem. So again, another thing which people are interested and concerned about is you have the holographic SMAR, which is precisely the Gibbs-Duhem relation in thermodynamics without d-dependent factors. But the bulk SMAR has these d-dependent factors. So what's going on there? Why do we have the bulk SMAR, with the d-dependent factors? And of course, this has in principle has nothing to do, well, the latter has nothing to do with holography, because you can have that in flat space and so on, and you will still have d-dependent factors. But yeah, I don't know. So that's another thing which people are, concerned about. So then, if we really allow, the CFT to be an arbitrary radius, and vary the volume by changing this radius there. So then the question is, this doesn't seem to correspond to anything in the bulk, right? So you just change the radius for the CFT, but what is changing in the bulk? I don't know, nothing, right? So do we really have the full dictionary there? And then, maybe you can tell me more about, like, we propose this mixed first law with the DC and with the center charge and the bulk pressure, but can this be really considered as a bulk thermodynamics? Maybe, probably not. So let me stop here, okay? Thank you. Oh, I'm 2 hours over time. Sorry for that.
2 hours? No, 10 minutes. But we asked you for more than 10 minutes, so I think that you made it in your time.
You're very kind.
No, of course. I mean, we usually interrupt a lot, but that's the point of having or inviting somebody to give a talk, right? If you don't want to interrupt people, then you just record them or go to some recording somewhere and then let them go, right? So, I mean, it's just as well that you overrun, because that's, as I say, that's the point. I have some questions, but I already asked a number of them. So if anyone else, I mean, I'm taking over the.
I have to run to pick up my kids from school, but it was great. Thank you very much, David.
Oh, thank you so much, David.
You might as well go with your question, Roberto.
Maybe I can begin with one question just to get it out of the way. I mean, you mentioned this thing of varying the Newton's constant, and as you said, this is something that you don't need a cosmological constant to do. You don't need anything. You could do it for the Schwarzschild solution in vacuum gravity, asymptotically flat. And I don't think that in that case it would make sense to vary the Newton's constant, right? Even if in principle you can do it, say that you want to write the first law in some. I mean, if you write and what do you get in that case that could make sense? I mean,
yeah, I don't know. I think these papers, they contain even number of mistakes, something like that. So so in the end, they claim that only with variable g you get consistency between SMAR and first law, but that's certainly not true. So I'm really puzzled by some of the statements. Yeah, I don't know. And in addition, they sort of like take some ingredients from the CFT. So I think we can safely ignore these papers probably. Well, you're gonna put this online, so let's not say that. But
maybe we can. I think that the recording, we should cut it at the moment when the seminar ended. That's something that people often do, and then during the
question. So then we are free to talk.
I think that's better, that you don't record later discussion. So as I was saying, I think that varying Newton's constant is something that if there's anything or if it makes sense in any sense, I think that you can always rephrase it in terms of something else. I don't see how it could be something that's physical in itself. And I don't think if there's any physics to it, I don't think that that's the clearest way of putting it. But the other thing, I mean, the variation of the cosmological constant, I think that's fine. Also, it came from the moment when David Mateos asked about the usual PDV term that we get for planar branes. In that case, that's well understood. That's just a conventional. I mean, we have a system that has a volume, and everything is extensive in that volume. And then in that case, we understand it. But this is different. And this volume that you have, if you have a spherical black hole, I mean, things are not extensive in that volume, or at least not in any conventional way. That's why I find that I don't know to what extent we were conflating the different PDV terms. So you had first, so there's, as I say, you have a planar black brane, you have a PDV term. You consider them, and the spherical black holes, you don't get a PDV term because that's you're not changing that. But then you were trying to recover that when you had this thing of, and in that case, let me say, I mean, when you consider that PDV term, the conventional PDV term, that's a PDV term where you only vary the volume. You're not performing you're not varying the time unit, the units of time, or you're not varying the normalization. So that's different. That's purely volume dependent. Later, when you were doing this thing of changing the conformal factor in the metric, in that case, you're then doing both things. You're changing the volume of the theory, but also the units of energy or the scale of energy. So I mean, that for me, that's been something that I'm not fully clear. I mean, how all of these PDV terms enter, which ones are
maybe you're right. Maybe that's
physically relevant or
that's a very good point, Roberto. That's right.
If as I say, in the usual way, I mean the usual and the planar black brane, the volume is just, I mean it's a planar black brane. You put it on some spatial torus, and then you change the size of the spatial torus, but you don't change the time direction. But you change it is just the spatial directions, which is what you would usually do for a normal.
Well, for the normal volume change. I agree with that perfectly. So you see, maybe there's something. Thanks. Something more to say.
I'm just that later. I mean, I was trying to relate the terms, and I got a little confused. I think, I mean, now that we're kind of we're off there, well, we're still being recorded. Can we stop the recording? Because I think that we'll all feel